The specific properties of beryllium. In this lecture, I will discuss about some anomalous behavior of beryllium. That beryllium is showing some of the properties which are not common for the other elements of the same group, right? So first point is that beryllium is extremely small. This is extremely small and have 2 unit positive charge, right? 2 unit positive charge. So this Be2 plus, right? So due to very small size and 2 unit positive charge and electronegativity, high comparatively in this group, high electronegativity. When I say high, means high in this group, high electronegativity. See, all these points or all these properties favors, right? Means small size, positive charge, high charge, you can say this, and high electronegativity compared to the other elements in the same group. This favors the formation of covalent compound. Covalent compounds. Even if you see in the BeF2 and in BeF2, the electronegativity difference between these two, delta En of beryllium and fluorine, if you compare, so it will come approximately 2.5. And if you compare beryllium oxide, so you have, it is delta En, you will have 2, right? So this favors the covalent compound, covalent nature. So the first point of anomalous behavior of this beryllium is that most of the compounds, or you can say all of the compounds of beryllium are covalent, while the compounds of other elements in the same group, they have sufficiently ionic character. Okay, so due to, and why the covalent character is prominent here in the beryllium compounds, that this is the reason. So these two reasons you can use. One you can formulate with the electronegativity difference, and other one, these three: small size, positive charge, high electronegativity compared to the other elements. So this is the reason why beryllium forms predominantly covalent compounds. Now the second point is, if you see the electronic configuration of beryllium, so this is 1s2, 2s2, 2px0, 2py0, 2pz0, right? So this is ground state electronic configuration. So this is the valence shell and no 2D is possible. So the maximum coordination number, of beryllium is 4. Means beryllium cannot form 6 bonds or 6 coordination compounds or compounds with coordination number 6 due to the absence of d orbital, right? So the maximum coordination number for beryllium is 4. In many compounds, this beryllium, suppose that this BeF2 is there, so vacant orbitals, due to the presence of vacant orbital, it has ability to form a compound like this, BeF4 minus, right? BeF4 minus, BeF2 2F, so this is 2 minus, right? BeF4 2 minus, or sometimes if you take BeCl2 in diethyl ether, Et2O, so this will form the compound But you know this BeCl2, this is in gaseous phase you are getting this in the monomeric form. But if it exists as this, so BeCl2 and ETO, ET, ETO, ET, lone pair, lone pair. So this kind of additional product is formed, right? So this is also see, if you can see here, the coordination number of beryllium is 4. So this type of compounds, this beryllium forms, and maximum coordination number is 4. In water, very interesting feature of beryllium we have observed, that in water, beryllium salts are hydrolyzed. Beryllium salts hydrolyzed and give a hydroxo complex right? And BeOH, OH, OH, 2 minus. So this is the hydroxo complex, and even more than this group are also can polymerize, right? So and you know, when you take this hydroxo complex, if you take this hydro complex in alkali, if you take this hydroxo complex in alkali, then this complex broken down, and you will get BeOH whole 4 2 minus unit, right? So if you take this in the alkaline solution or in alkali, then you will get mononuclear complexes, and again with the coordination number 4. Here also the coordination number 4. So this is some of the important properties of what beryllium compounds. And one more important thing, that if you take this beryllium, hydrated beryllium salts, so these hydrated beryllium salts acidic in nature if you dissolve it in pure water. So next point is, the next important feature is that the beryllium salts are acidic when dissolved in pure water. When dissolved in pure water. Because you know, if you take Be2 plus, so Be2 plus in aqueous medium, what is the better way to write Be2 plus? In aqueous medium, you should write this like this, BeH2O whole 4. Because you know, every ion has this feature in aqueous medium, if it has small size and have charge. So all of you are knowing that transition elements they have very small size compared to the S block elements, and high charge density. Due to that, they are hydrated, and every transition metal ion exists in this form of hydrated complex, right? So in water, every small and charged ion has this feature, means it is always hydrated. As I have already explained that transition metals, they are always hydrated. Okay. means different number of water molecules as per the coordination number, preferred coordination number of water molecules surrounded the metal ion. Now this beryllium 2 plus, this interacts with water, this hydrated ion BeOH2 whole 4 2 plus H2O. So this will give us BeH2O whole thrice OH and plus 1 plus H3O plus, means this ion loses H positive, this will give H positive. So one of the water molecules. So how we can visualize this? You can see that BeOH, this is the hydration of this OH2, OH2, OH2. This is the type of bonding here, Be2 plus. So due to very small size of this beryllium 2 plus and high charge density, this is very much electronegative as well. So what will happen? This will attracts the bond pair of electron and H plus will go here. And beryllium oxygen bond, this is very strong bond, sufficiently strong bond. So from here this will release H plus. So this H plus is released like this. This H plus is trapped by water, so H3O. So this solution is acidic basically. Acidic. So due to this autoprotonation of this water molecule, basically the water which is coordinated with the central metal atom, and this phenomena you will have for every metal which have ability to form a strong bond with this oxygen, right? Then they will show this acidic nature, and many of your aluminium also shows this behavior, and iron also shows this behavior. So many metal ions have this ability to show this type of acid base reaction, right? So this is also one of the property which is shown by the beryllium. And one more important point is that beryllium and aluminium shows the diagonal relationship. So beryllium and aluminium, like aluminium, beryllium is also amphoteric, right? So beryllium is amphoteric. Amphoteric means this reacts with, beryllium reacts with alkali and forms what? Hydrogen, right? So what exact reaction, if you want, you can write Be plus NaOH. So you have BeOH whole 4 Na2, 2 minus is here, so Na2 BeOH whole 4 plus hydrogen, right? So this is the exact reaction, as aluminium also showing this type of reaction. And aqueous medium is required here, so water also we can write here. Plus H2O, because H2O is the part of this reaction. So now you can balance this 2 and 4 oxygen, 2 and 2. So this is the balanced equation, right? So sodium berylate, you are getting here sodium berylate. One more form, one more way to write this, you can write Na2 BeO2 dot 2H2O. So in this form also you can write this, right? So beryllium is amphoteric and and it is diagonally related to aluminium, right? Diagonally related to aluminium. Okay. Similarly, if you take beryllium hydroxide, BeOH whole twice, it is also amphoteric. Beryllium oxide, this is also amphoteric. So if a metal is amphoteric, then its hydroxide is amphoteric, then its oxide is also amphoteric. The same thing, this will apply in the whole, inorganic chemistry. Okay. One more important property that if you take beryllium, so beryllium rendered passive by nitric acid as aluminium, right? As aluminium. So like aluminium, beryllium also becomes passive with nitric acid, and this has the diagonal relationship with aluminium. So all those properties are shown by this, right? And beryllium salts among the most soluble in this group. Beryllium salts are among the most soluble. This is due to the small size of this, and there is a thumb rule. If there is a large difference in the size of cation and anion, generally salts are soluble. This is a very, very important rule. If there is a large difference, so salts having large difference in the size of anion and cation, are soluble in water. This is very, very important generalization, and this is because in this situation delta H hydration dominates over delta H lattice, right? Delta H lattice. So this is the the ideal condition or thermodynamic condition for the solubility. So beryllium is smallest. So if you take any of its anion, whether it is chloride, sulfate, nitrate, are also always soluble, carbonate, whatsoever you are taking, all are soluble. So this is very, very important theoretical generalization, and this will help you to solve many objective questions or questions based on the logic. You can very easily solve by using this concept, right? And complex formation, beryllium form complexes, but other elements do not form. So all these we are knowing here, but although I am writing here, beryllium has maximum tendency to form complexes in the group, right? So, and this basic beryllium acetate, basic beryllium nitrate, I have already explained this in the lecture. Okay, good. Now I will take up some of the important compounds, preparation of some of the important compounds, and then this S block will be over. Now see, solve or ammonia soda process for the preparation of basically sodium carbonate. So sodium carbonate, this is a very useful compound, industrially very important compound. So process, this is for sodium carbonate, right? This process is used for the preparation of sodium carbonate. And industrially, this is very important compound. It is used in glass industry and in the soap industry, right? See, the overall reaction of preparation of this, overall reaction is this: NaCl plus calcium carbonate. This will give you sodium carbonate plus CaCl2. This is overall reaction, right? This is overall reaction, but you know this, and these are the chemicals which are consumed. These two chemicals are consumed, but don't think that by using these two chemicals only we are going to prepare. Some other chemicals are also required, but those chemicals are reused in this process, right? So the overall reaction is this. So the reagents, the compounds which are consumed, so these are consumed, and there is no direct reaction between these two, right? But this is overall reaction. This is overall reaction. This is not the direct reaction that you will mix sodium chloride and calcium carbonate and get the sodium carbonate and calcium chloride. Direct mixing, this will yield, the yield of this reaction is very, very poor, right? So very careful. Method, I mean, we should very careful to in the preparation of this sodium carbonate. So these two chemicals, basically they are consuming. Other chemicals are also used, but they are reused in this equation. So see, the overall reaction is this, I mean overall reaction, or we can say net reaction, right? Now see the detailed mechanism, detail of this, detail reactions. So in the detail reactions, first we are taking this ammonia plus H2O plus carbon dioxide. So they will react with each other and produces ammonium bicarbonate, right? In the reaction condition, they reacts with ammonium bicarbonate. So see, none of this chemical is here in this reaction. Now sodium chloride, use here sodium chloride plus ammonium bicarbonate, NH4HCO3. So we want to prepare here sodium bicarbonate. As all of you are knowing that the sodium bicarbonate exists as a solid state, because you know bicarbonate infinite units are linked together through hydrogen bond, and therefore we can easily filter out this sodium bicarbonate. So NaHCO3, this is solid, plus NH4Cl, right? Now this sodium bicarbonate, on heating, NaHCO3 on heating 150 degrees Celsius approx, you will have sodium carbonate plus carbon dioxide plus H2O. So these are the main reactions. This is reaction 1, this is 2, and this is 3. So you will get sodium carbonate, right? And now see, you can see here that this carbon dioxide which is produced here, this is also reused here. Now see here, ammonium chloride we have as a side product. So from ammonium chloride we can get ammonia, this ammonia. How? All of you are knowing what? Any ammonium salt on reaction with the alkali or base, this will produce what? Ammonia. So the second, still we have not used this calcium carbonate. Now see, the rule of calcium carbonate starts. Now this calcium carbonate on heating produces calcium oxide plus carbon dioxide, and this calcium oxide plus water, approximately 1100 degrees Celsius, this will decompose. This with water, this will produce calcium hydroxide, and this calcium hydroxide on reaction with this ammonium chloride, this will give ammonia plus CaCl2 plus H2O, right? Now see, now you can see that this ammonium chloride, what is here? This ammonium chloride is used here, and this ammonia which is produced, that is again recyclized and used here, right? So ammonia is reused, carbon dioxide is reused, okay, and so here ammonia and carbon dioxide, they are reused. So see how this sodium carbonate is prepared by this method in a good yield. We are taking sodium chloride and calcium carbonate in a different steps, not together mixing, we are mixing. So if you add all these equations, you will get cancelled all these things, only this calcium carbonate and sodium chloride is there. So basically the consumable chemicals are here, calcium carbonate and sodium chloride, right? And all other chemicals are reused, right? So this calcium carbonate on heating, this will produce carbon dioxide. This carbon dioxide also reused here, right? So this is the method of preparation of sodium carbonate by this method, and this is a commercial method of preparation of this, right? Can we prepare potassium carbonate by this method? Can we prepare? So you cannot prepare potassium carbonate by this method, because this potassium bicarbonate, what you are getting, that is more soluble, right? So due to the solubility difference, it is very difficult to prepare potassium carbonate by using this method, right? And one more important property of this hypo solution, that is it is used in the iodometric titration, but it is a secondary reference, right? Secondary standard. So can be used as a secondary standard solution for titration, for iodometric titration, iodometric or ID metric, iodo and ID metric titrations, right? So secondary standard means on standing, the concentration of this solution will change. On standing, the concentration of this solution will change. So see, preparation of sodium thiosulfate. First preparation we can take up, if excess of sulfur is treated with NaOH, so you will have Na2S plus Na2S2O3 plus H2O, right? 4, 6, 2, 3. Similarly, if you another method, if you take sulfur plus Na2SO3 sodium sulfide, so they also on reaction you will have Na2S2O3, right? And industrial method of preparation or commercial method, you can say industrial method. Method of preparation is, if you take Na2SO3 sodium sulfide, Na2SO3 plus I2 plus Na2S. So this will give you Na2S2O3 plus NaI, right? So this is a commercial method. Now see, heating effect on this, heating effect. So Na2S2O3 dot 5H2O on crystallization, we will get the water of crystallization here on heating 315 degrees Celsius. Na2S2O3 dot 5H2O, dehydration will take place, and if you further heat this, further heating, so you will have Na2S5 plus Na2SO4, Na2SO4, right? So at high temperature, basically high temperature is required. So this is a polysulfide, basically polysulfide and sodium sulfate. So okay, and now see decomposition. If we take Na2S2O3 plus HCl, so with acid this will decompose to NaCl plus SO2 plus H2O plus S, right? So this will decompose with acid. If you take H2SO4, so with H2SO4 also this will decompose. Dilute acid, you should take dilute acid, HCl or H2SO4, whatever you can take, you will get sulfur dioxide gas, and this is a colloidal sulfur, right? So acid or HCl, okay. Now this Na2S2O3, this is used to remove excess AgBr from photographic plate, right? So Na2S2O3 plus AgBr, this will give you Ag2S2O3 plus 2NaBr, right? And this Ag2S2O3 with the moisture, this will form Ag2S black precipitate plus H2SO4, right? And if you take this Ag2S2O3 plus Na2S2O3 excess, so you will have complex like Na3 Ag S2O3 whole thrice, right? So this complex you will get, and in gas, okay. And other use of this, so this is additional reaction basically. This is additional reaction of this. These two reactions were used in the photography to remove silver bromide from the photographic plate, right? And this question is asked in JEE Advanced as well. So this is very important relation. And it is also used in the iodometric titration. See, Na2S2O3 plus I2, you can in acidic medium you will have Na2S4O6 plus NaI. So iodometric, this is iodometric titration. So this is the use of this hypo solution in the photography, traditional photography, where films are developed. So AGBR is used, which is a photosensitive molecule, and that excess AGBR is removed by making this soluble salt, right? This is salt and it is soluble. And second one is the iodometric titration. I2 can be titrated. So how this I2 will get? Any oxidizing agent, if we take and Ki. So in oxidizing agent and Ki, reaction of this will produce I2, and this I2 is titrated with this hypo solution, right? What is the indicator here? The indicator is starch, freshly prepared starch solution. So in this way you can prepare, you can titrate and you can calculate the oxidizing agent, quantity of oxidizing agent by this iodometric titration. So first your oxidizing agent reacts with Ki to produce I2, and this I2 is titrated against this high standard solution, right?